Good morning all. Today we are going to study the topic characteristics of DC generator. It is this characteristics which determines the suitability of a generator for a particular purpose. They are obtained by making simultaneous measurements of terminal voltage and load current using voltmeters and ammeters. Generally, three characteristics of DC generators are taken into considerations. They are no load saturation characteristics, internal characteristics and external characteristics. We have to study each one of them in detail. No load saturation characteristics is also known as open circuit characteristics, that is OCC. It is also said to be magnetic characteristics. This characteristics gives the relation between no load generated EMF and the field current. The relation for no load generated EMF we all are quite familiar. We have studied the derivation of that in our previous sessions. That is E0 is equal to 5PNZ by 60A. This no load saturation characteristics is just a magnetization characteristics, or I can say it as just a magnetization curve. The internal characteristics or total characteristics gives the relation between on-load generated EMF and armature current. On-load EMF is represented by E, and the magnitude of this E is always less than that of the no-load generated EMF E0. This is due to the adverse effects of armature reaction. The last one is external characteristics. It is also said to be performance characteristics. It gives the relation between terminal voltage and load current. Terminal voltage is represented by V here and the load current is represented as I. The magnitude of V is less than that of E due to the voltage drop in the armature circuit, that is IARA drop. We are going to study in detail of this characteristics for different types of generators. That is for separately excited generator, series generator and shunt generator. First we are going to study about the OCC of a separately excited DC generator. The data for OCC characteristics is obtained by operating the generator at no load and keeping at a constant speed. The circuit arrangement to plot the OCC is indicated here. From the diagram it's very clear that it's a separately excited DC generator. A voltmeter is connected across the terminals of the armature and an ammeter is used to measure the field current. The field current is varying by using this potentiometer. From this diagram it's very clear that there is no load connected in the armature. In order to plot this OCC, the field current is varied by adjusting this potentiometer and the corresponding magnitudes of generated EMF are obtained from this voltmeter. While conducting this test, the speed of the machine or the speed of the DC generator is maintained at a constant speed. From the relation of generated voltage, we very well know that it is directly proportional to the field flux. Therefore, if we are increasing the value of this field current, then consequently the magnitude of this induced EMF also increases. That can be seen very clearly from this characteristics. You are increasing the value of field current and the magnitude of no load generated voltage is also increasing. Next we are going to study the internal and external characteristics of a separately excited DC generator. The circuit arrangement to plot both the internal characteristics and external characteristics is shown here. From this diagram it's very clear that the magnitude of load current is same as that of the armature current. While plotting the internal and external characteristics of the DC generator, that is the separately excited DC generator, the speed and field excitation of the DC generator is maintained at a constant value. In order to plot the internal characteristics, that is the characteristics between on-load generated EMF and the armature current. First, the characteristics between no-load generated EMF and the armature current is plotted. That is this line 1. From the magnitude of E0, we will be reducing the value of armature reaction drop to obtain the magnitude of E. As we all know from the previous session, when the magnitude of armature current is increasing, definitely the effect of armature reaction will also increase, which results in more the value of armature reaction drop. It can be seen very clearly from this characteristics. As we are increasing the value of Ia, the magnitude of this armature reaction drop is also increasing. The armature reaction drop which you see for the small value of Ia is not the magnitude when you are increasing the magnitude of Ia to a larger value. That is, as we are increasing the magnitude of Ia, the armature reaction drop's magnitude is also increasing. From the circuit arrangement, we will not be getting the magnitude of E as a measurement in any of this voltmeter or ammeters. That is, we won't be getting the magnitude of E or the value of E as a reading in the circuit arrangement. Now let's see the external characteristics. The external characteristics is plotted between the terminal voltage and the load current. In the case of a separately excited DC generator, the magnitude of line current is same as that of the magnitude of armature current. Hence the magnitude of load current can be measured from the same ammeter which we used before for the measurement of armature current. So in order to plot the external characteristics, we will be varying the load and hence this load current, and the corresponding values of terminal voltage are measured from this voltmeter. Then the characteristics are plotted between these two readings, and it is said to be the external characteristics. It is also said to be performance characteristics or load characteristics, and it is shown here very clearly, the characteristics between this V and Ia, and it is indicated as line number 3. Next we are going to study the no load characteristics of a self-excited generator, in specific a DC shunt generator. In order to obtain the OCC of a DC shunt generator, the field winding of the DC shunt generator is disconnected from the machine and connected to an external source of DC supply as shown here. This is actually the field winding of the generator, that is shunt generator. It has been disconnected from there and connected to an external DC source arrangement. We will be able to vary the magnitude of field current by making adjustment in this potentiometer, and hence the corresponding magnitudes of no load EMF can be obtained from this voltmeter. The characteristics which is being plotted between this ammeter readings and this voltmeter readings is said to be the OCC, and that has been shown here. Comparing with the OCC of a separately excited DC generator, which is shown here, in this OCC, some EMF, that is the magnitude OA, which is represented here. So some EMF OA is generated even when the magnitude of field current is 0. At this point the magnitude of field current is 0, and even when the magnitude of field current is 0, there is some EMF which is being induced or generated. This is possible due to the presence of residual magnetism in the poles. This residual magnetism is actually a small amount of magnetic field which is being present in the iron cores of the shunt fields even when the generator is in rest condition. It is in fact the leftover magnetism from the previous cycle of operation of a self-excited generator. So due to this residual magnetism, even when the magnitude of field current is 0, a very small magnitude of EMF gets induced, that is represented by OA. So it's very clear that comparing with the characteristics of the separately excited DC generator, the OCC here starts a little way up, that is from this point A, like this. It doesn't start from the origin just like that of a separately excited DC generator. Next, all of you must know the concept of critical resistance associated with a shunt generator. Critical resistance is actually the term which is being used for the resistance of shunt field winding. In the previous slide, we have studied the concept of residual magnetism. Due to this residual magnetism, some EMF gets induced initially and hence some current. This current, while passing through the field coils, will magnetize the poles further. As the poles are more magnetized, it results in increased value of generated EMF. As the magnitude of induced EMF has been increased, this will further increase the magnitude of field current, and the mutual reinforcement between EMF and the flux carry on till an equilibrium point is reached. If you see in this characteristics, an OCC is plotted and numerous resistance lines are drawn. The resistance lines are indicated as OL, this is actually L, OL, OC, OA and OB. Suppose the resistance of shunt field winding is R, then the corresponding equilibrium point will be the intersection of this OCC and the resistance line, that is the intersection point of this OCC and the line OA, that is actually the point P. This is the equilibrium point. So till this equilibrium point, the mutual reinforcement between the flux and the generated EMF takes place. If you are seeing here, comparing with the resistance values of line OA, the resistance values of line OC and line OL are more, whereas the resistance magnitude of line OB is smaller. As we are increasing the magnitude of resistance R of shunt field winding to a very large value, then definitely the magnitude of field current will be quite small, which won't be sufficient to cause the field excitation. That is, the machine will fail to excite and there won't be any buildup of voltage when the magnitude of field resistance is very large. So there is a limiting value of resistance, that is the shunt field winding resistance, which allows the field winding to excite. If the resistance value is increased beyond that value, then definitely the machine will fail to excite and there won't be any generated EMF. That particular limiting value of resistance is said to be the critical resistance for shunt generator. The value of critical resistance can be obtained from the OCC by drawing a tangent to it and obtaining its slope. If you are looking here, this is actually the OCC and the tangent which is being drawn is OC, and if you are taking the slope of this OC, that will give you the particular value of this critical resistance. This concept of critical resistance is a very important one. You have to use this in the problems also. We will see this problem in the next session. Now let's see the external characteristics of shunt generator. The circuit arrangement to plot the external characteristics is shown here. External characteristics is actually plotted between the terminal voltage and the load current. In order to measure the terminal voltage, this voltmeter is used, and the load current, this ammeter is used. So external characteristics is plotted between the measurements of this voltmeter and this ammeter, that is ammeter A2, and it is being shown here. In order to plot the external characteristics, we have to increase the magnitude of load current. The magnitude of load current is increased by reducing the magnitude of load resistance. The magnitude of load resistance is decreased by turning on these switches. Whenever more number of switches are being turned on, this indicates that more number of resistances will be connected in parallel. As you are aware, when the number of resistances connected in parallel are increasing, then definitely the effective value of resistance will get reduced. The same concept is being used here. As you are switching on or as you are turning on more number of the switches, then more number of resistances will be coming in parallel. This will effectively reduce the value of load resistance, which further increases the magnitude of this load current. As we are increasing the magnitude of this load current, definitely the magnitude of terminal voltage keeps on decreasing. This is mainly due to the armature reaction drop and armature resistance drop. Both the magnitude of this drops goes on increasing with the increased value of load current. This phenomena continues till point B is reached while delivering a large magnitude of load current OB corresponding to this point small b. If you make any attempt to further increase the current, that is the load current beyond this point B, then you will be able to see an unusual behavior that is shown here. If any further attempt to increase the load current beyond this point will result in a very rapid decrease in the terminal voltage, and this causes the characteristics to turn back like this from point B to point C. As you make any attempt to increase the load current from this point, then all of a sudden the magnitude of terminal voltage goes on decreasing and finally it comes to zero value. This is happening due to the severe armature reaction drop and very large magnitude of IARA drop, that is armature resistance drop. Due to this large magnitudes of these drops, the magnitude of terminal voltage is also very much reduced. Hopefully the external characteristics is also clear for you now. Next we are going to study the internal characteristics of DC shunt generator. That is the characteristics which is plotted between on-load generated EMF, that is represented as E, and the armature current which is represented as IA. The internal characteristics line is actually obtained from the external characteristics here. We have already studied how to plot the external characteristics in the previous slide. The same is represented here by the line AB. Here if you see another line OB is drawn. This line OB is just like the field line resistances which has been drawn in the case of OCC as shown here. That is just like how we are drawing the line OL, OC, OA, OB. This line OB is drawn here. This indicates the field resistance line. Hence the horizontal distance of this line OB from this line vertical line OA indicates the values of field current for different terminal voltages. So if we add these distances to the corresponding magnitudes of this terminal voltage, horizontally we will be adding it, then we will be getting a new line which is indicated as this dotted line, that is AC. So this AC indicates the curve of total current. If we add the IARA drop along with this AC vertically we will be adding the IARA drop. Voltage drops has to be added vertically and the magnitude of currents has to be added horizontally. So if we add the IARA drop vertically along with this line AC, then you will be obtaining the internal characteristics, that is the characteristics which is between E and IA. This is how the internal characteristics will be obtained from the external characteristics. Now we are going to study the characteristics of a series generator. So far we have studied the characteristics of shunt generator. In the series generator, if you see in this diagram, it's very clear that the magnitude of armature current is same as that of the field current, which is same as that of the load current. Even though in all these characteristics, if you see in the case of OCC, you are plotting between E0 and the field current. In the case of internal characteristics, you are plotting between E and armature current, whereas in the case of external characteristics, you are plotting between the terminal voltage V and the load current. So even though the currents in all these characteristics are different, in the case of series generator, This all currents are one and the same. Hence all the characteristics can be plotted by using a simple graph or a single graph. You don't need to plot each separately, just like how we have been plotted for the case of a shunt generator. So initially OCC is drawn, just like how we are drawing the OCC for the shunt generator. We will be disconnecting the series winding and will be connecting it as a separate, will be connecting it along with the separate DC source, and then we will be obtaining the OCC, that is the characteristics which is being plotted between E0 and IF. In order to plot the internal characteristics, armature reaction drop will be subtracted from this OCC, and then we will be getting the characteristics between E and IA. IA is same as that of IL is same as that of IF. Next we have to plot the external characteristics. For that we will be subtracting the magnitude of armature resistance drop from this internal characteristics. So the characteristics OC is the external characteristics. Just like in the case of a shunt generator, if you are trying to increase the value of this load current beyond a particular value, then definitely due to the severe armature reaction and a very large value of armature resistance drop, the magnitude of terminal voltage starts decreasing and goes to 0, as represented by a dotted line here. So you must be very careful that the magnitude of load current should never be increased beyond this particular value. Then it creates an unstable condition. If you are increasing the load current to a value OC dash, then the magnitude of terminal voltage will be 0, as you can see from this characteristics. With that, we have completed all the three characteristics for all these three different types of generators, that is separately excited, shunt and series field generator. Next we are going to study the applications of these types of generators. The suitability of a particular generator for a particular application has been decided from their characteristics. As you see the characteristics of a DC shunt generator, the terminal voltage almost remains constant, hence it can be used for charging batteries and for any other applications where the terminal voltage is a constant one. In the last slide we have seen the series generators are having a rising characteristics. See, you have seen here, this is actually the external characteristics and it is actually a rising characteristics. This rising characteristics makes it suitable for the applications of boosters. Next we are going to study the applications of compound generators. Even though you haven't studied the characteristics of compound generators, you must know the applications of compound generators. As we have discussed in the types of DC generator session, compound generators are classified into cumulatively compound and differentially compound. The characteristics of differential compound generator is very much similar to that of a DC shunt generator, but with larger demagnetization armature reaction, due to which there will be large drops here. In the case of a differential compound generator, the characteristics remains almost similar. The only difference is this drops magnitudes will be very large. Hence they are used for arc welding applications where large voltage drop is required when the magnitude of currents is very large. The cumulative compound generators are used for applications which require a constant DC supply. Example, lamp loads and heavy power supply for electric railways. With this, we are completing today's session. Thank you.